Hello, everyone. Welcome to the Types of Databases lecture. We are going to first dive into the data storage systems that power the majority of software applications and services that we rely on every day. So we're gonna start with the basics. What is a database? So a database is an organized collection of data that is stored and accessed electronically. And databases allow us to store vast amount of information, retrieve specific data quickly, and also maintain integrity and consistency over time. Why databases are essential? It's because databases have be basically become the backbone of modern technology. So, social media platforms that you are aware of, banking systems, and online retailers, they all rely on databases to manage user data, also manage transactions and interactions. So, depending on the nature of the data and the application's performance or scalability needs, uh, developers and application architects, they choose from a variety of database types. So, in this lecture, we're going to look at the main categories. They are relational databases, and several form of NoSQL databases such as key value databases, document databases, column family databases, and graph databases, as well as relatively a new one, which is called NewSQL. Also, we're going to talk about in-memory and cloud databases. So by the end of this lecture, you should have a good understanding of how each type of database work, the benefits they offer, and when to use them. Now, relational databases, also called as SQL databases. So relational databases are the oldest and most traditional form of modern database systems. Relational databases, they store data in tables composed of rows and columns. And you can think of it as an Excel spreadsheet. And each table, they typically represents a real world entity. What do I mean by entity? You can think of entity as customers, orders, and products, and you would have each create table for each entity. And each row, they represent a unique record. So if you're creating a customers table, each row of the customer table will represent a single customer. And one defining characteristics of relational databases is the schema. And what does what do I mean by schema? You can think of schema as a strict blueprint of how data is organized and how tables relate to one another. And this schema uh, enforces consistency. So basically ensures that each column contains the correct type of data and that relationships between uh, tables remain intact. And SQL, which is a structured query language, is the language used to interact with relational databases. We're going to talk about SQL more, but just know that SQL offers commands to retrieve data by using select keyword, modify data using insert, update, delete, and handle database structure by creating table, altering table, etc. And Common relational databases you might have encountered include um, MySQL. MySQL is open source and widely used database for web applications. And another very similar open source, widely used database is PostgreSQL, uh, but it's also known for its advanced features and extensibility. Uh, Oracle database is popular in large enterprises, and Microsoft SQL Server uh, is popular because it often integrated with other Microsoft products. Although there is a recent rise of alternative database models, relational databases continue to be favored for applications that require strict consistency and well-defined data relationships. Next slide, NoSQL databases. So in contrast to relational databases, NoSQL, NoSQL, by the way, is often interpreted as not only SQL. Uh, these databases offer more flexible data models compared to relational databases and are built to handle large volumes of data across distributed systems. These NoSQL databases, they kind of emerged as a response to the limitations of the relational model in scenarios requiring rapid scalability and high availability. So, unlike relational databases, NoSQL databases do not stick to a fixed schema. Uh, so, this makes them ideal for handling unstructured or semi-structured data. Uh, some of the examples of unstructured and semi-structured data are logs, social media content, or sensor data. Moreover, many NoSQL systems can efficiently scale horizontally by adding more hardware, which is not such an easy thing to do if you have a relational database. So this makes NoSQL systems particularly appealing for applications with large scale or rapidly growing data sets. And within NoSQL universe, you can divide into four main categories. First would be key value database. Second would be document database. Third, column family. And fourth is graph databases. And each category addresses specific use cases. I know we're going to talk more about it in subsequent slides, but just to give you an overview, uh, a key value store handles session data really well, while a graph database uh, handles and does really well at analyzing complex relationships such as social network, and some popular NoSQL systems include MongoDB. This is known for its document storage, and Cassandra, which is a column family database, and Redis key value, famous key value database, and Neo4j is a well-known graph database. So let's look at each of these categories more in detail in the next slide. Let's first look at key value databases. Key value databases store data in the simplest possible form. You can think of a dictionary hash map data structure. Uh, so each record consists of a key key being a unique identifier and a corresponding value. And this corresponding value can be any type of data. It can be string, can be JSON, binary, and so on. So this key value lookup structure allows for extremely fast lookup. So this is used when data retrieval is important. And because of this property, key value databases are often used for caching, session management, and other scenarios that requires really quick reads and writes. To give you an example, let's think of web applications. Then a lot of web applications would have uh, user login, and these applications need to store user session information. And key value databases like Redis is used to retrieve that information uh, rapidly when a user loads a page. And key value databases can be highly scalable uh, because as your application grows, you can just simply add more nodes to distribute the load. So this data model simplicity means fewer overheads when you need to store new types of data. However, key value stores, they typically lack the advanced querying capabilities of relational database that you may be familiar with, or even some other NoSQL data models. So because of that, it's difficult to easily filter or aggregate data based on properties inside the value unless you index or structure it in special way. Moving on to document databases. Document databases store data in the form of documents, uh, in often using formats like JSON, BSON. So each document typically represents a single entity, and you can think of single entity as like a user profile or product description, uh, which means this description can or user profile can contain nested structure, and this is more flexible than the uh, rows and columns of a relational database, which uh, are often too rigid, and different documents in the same collection can have varying fields. So, um, significant advantage of document databases is how well they map to modern programming paradigms. So, for example, say you are developing in JavaScript, uh, then you will often use JSON because JSON stands for JavaScript Object Notation. So, and that means you will store data in JSON format. And if you use document database, you can basically retrieve this information without needing to transform between the database and your code structure. And this can be really helpful uh, in terms of boosting developer productivity and reducing code overhead. And MongoDB uh, is really popular prime example of a document database, and it's frequently used for content management system, real-time analytics, mobile apps, and e-commerce platforms. CouchDB is also another well-known document store that uses JSON, and you can, uh, it has a really nice replication feature. And because of these document databases' flexible schema, they can adapt easily to changes in your data model. So if you need to add new fields to your documents or store new types of data, there's usually no downtime required to modify the schema. Next, column family databases. So column family databases store data in a structure that groups related columns together rather than storing them in fixed rows. So this means each row can contain a variable number of columns, which are grouped into column families. And this column family database model kind of emerged from Google's big table design and later was made popular by open source systems like Apache, Cassandra, or HBase. So, what is the advantage of this types of databases? Uh, these databases excel in write-intensive scenarios where you have to record large volumes of data at high speed. Uh, so examples would be uh, such as like log aggregation or storing sensor data or doing like a real-time analytics. And, and these databases scale horizontally across many servers really well. Uh, what I mean by that is you can just keep adding more nodes to manage increasing loads. So by storing related columns together, column family databases can achieve very efficient data compression and rapid reads, especially if your queries typically like focus on retrieving related columns. W- What do I mean by that? Just to give you an example, say you only need to read a few columns from a really large data set. Uh, uh, what column family databases can do is uh, reduce I/O, input and output, by reading only the relevant segments. However, their complex internal structure can be more challenging to design and manage compared to simpler data models. So you need to plan how to organize your columns and row keys to ensure you get the performance you desire. Let's move on to graph databases. So graph databases represent data as nodes, or you can think of it as nodes as entities and edges as relationships. So each node can have properties such as key value pairs, and each edge can also have properties. So uh, defining the nature of the relationship between nodes. And this type of databases are used a lot uh, when you're in a scenario where relationships are central to the data model. And the prime example would be social network, where you want to quickly see who is connected to whom. Another one would be recommendation engines, where you track user interest and product categories. In these use cases, the complexity of relationships can make traditional queries in a relational database slow and cumbersome? It's because in order to find out in a relational database, it will involve numerous join operations. However, in a graph database, uh, relationship traversal is direct and highly efficient. And Neo4j is a popular open source graph database known for its Cypher query language. And Cypher query language allows you to describe patterns in your data just as you would visualize them in a graph. There are other systems, uh, Amazon Neptune, Janus Graph. They also follow a similar data model. So they often integrate well with big data ecosystems. And graph databases, what they do really good job of answering questions like uh, finding the shortest, can you find the shortest path between these two nodes? If we are to give some business context, you can think of questions like, say you have customers, which customers follow the same topics as this particular customer? Uh, and these databases can find the answer to these quickly and elegantly. And however, if your application deals primarily with tabular data or simple key lookup, uh, it might be overkill to have graph database. It's probably not worth uh, bearing that overhead. Moving on to new SQL databases. New SQL databases, what they do is they attempt to bridge the gap between the strong transactional consistency of SQL relational databases and the horizontal scalability of NoSQL systems. Uh, as you might recall, traditional relational databases, uh, they they are often constrained by a single node or even if they have more than one node, they will have limited cluster design, while many NoSQL systems, they relax consistency to achieve scalability. So what this new SQL databases are trying is to bring the best of both uh, SQL relational databases and NoSQL systems. So these new SQL databases have ability to maintain ACID properties. What we mean by ACID is A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. This is really important property uh, for maintaining consistency, and new SQL has the ability to maintain this property across a distributed architecture. And this can be uh, really appealing uh, if you have an application that has a requirement uh, that has strict requirements which does not allow you to afford data inconsistencies. At the same time, you need to handle a massive volume of transactions. And uh, Google's Spanner database is a pioneering example. This Google Spanner is used internally at Google to handle a huge scale of data with global consistency, which is not possible in a traditional relational databases or traditional NoSQL systems. After Google Spanner, there are new SQL databases such as CockroachDB or VaultDB. They each have slightly unique approaches to sharding, replication, and transaction handling. So while new SQL systems can be more complex to operate than a single node relational databases, they solve scaling challenges that are critical for companies dealing with large user bases and workloads. Now, let's move on to in-memory databases. So, in-memory databases keep their primary datasets in main memory. If you're familiar with your laptop internals or desktop internals, basically datasets are kept in RAM uh, rather than disk storage. So accessing data in RAM is significantly faster than accessing data on disk storage. I would say by orders of magnitude. Um, so as a result, in-memory databases can handle uh, real-time analytics and um, high-frequency trading or any other low latency tasks. One common use case is caching results that would be really expensive to compute or retrieve repeatedly. Just to give you an example, say you have a web application, and if your web application runs queries against a slow data source, you would benefit from storing these data that you retrieve from these queries in an in-memory system like Redis to make subsequent requests really, really fast. SAP HANA is an enterprise-grade relational in-memory database. Uh, it's pretty unique and special because it not only is an in-memory database, but it supports complex SQL queries. Redis is more popular. It is often, Redis is often called a key value store, but you can use this key value store as a full in-memory database. So Redis offers data structures like list, sets, and sorted sets. So one thing to keep in mind uh, with in-memory databases is that they usually require uh, enough RAM to store your working data sets. So hardware cost and the cluster design can become quite concern if you have large applications uh, that needs to store a lot of information in RAM. Moving on to cloud databases. So cloud databases are offered as managed services on platforms like Amazon Web Services, Microsoft Azure, Google Cloud Platform. Instead of manually installing and maintaining your database servers, you rely on the cloud provider to manage the underlying hardware. Uh, Not only managing the underlying hardware, uh, cloud provider would manage patches, backups, as well as scaling the database. So this approach is often referred as database as a service, and the main benefits are convenience and scalability. You can basically spin up a database instance with just a few clicks or via an API call and scale it up or out as your data or traffic grows, which is not possible if you're using on-premise database. In order to do that, you have to buy hardware. So uh, if we kind of go into pricing, pricing typically follows a pay-as-you-go model, which means you only pay for what you use. And some prominent examples include Amazon RDS, and Amazon RDS supports a lot of famous relational databases such as MySQL, PostgreSQL, Oracle SQL Server, MariaDB, and Amazon's Aurora database, and Azure Cosmos DB uh, is also quite popular, uh, and it's known for its globally distributed multimodal database, and Google Cloud Spanner, which we briefly talked about when we talked about NewSQL. So it's a globally distributed relational database, and using these services can significantly reduce operational overhead. So if you are, uh, say, if you're in a company with small development teams, it really makes it easier for development teams to focus on their application logic instead of managing infrastructure. Choosing the right database. So we looked at a lot of database options, and you might wonder, how do you choose the right one? Uh, it really varies on cases, but I would say the first step would be looking closely at your data structure. So for the app you want to build, is your data structure highly relational and structured, or is it more flexible and varied? Uh, that's the question you can ask. And then um, you also want to see whether you need to rely on complex joins or whether you need transactions with strong consistency. If that is the case, uh, a relational or new SQL databases might be your best bet. If you're dealing with unstructured or uh, really fast growing data and require high scalability, if that is the requirement for your application, you might want to look into NoSQL databases. So you and after that, you want to consider the trade-offs around performance and consistency. So some of these systems, what they do is they sacrifice strong consistency guarantees to achieve better performance at scale, whereas others maintain strict asset compliance even in distributed setups. So you want to weigh factors like scalability and budget. And cloud databases can reduce maintenance cost and complexity, but they might become expensive at very high usage level. On the other hand, self-hosting can be cheaper in the long run, but requires in-house expertise. And finally, you want to think about your development team's familiarity. So, are you and your developers familiar in SQL, or do they prefer a more flexible NoSQL data model? So, you want to weigh whether it is important to adopt uh, with whether the necessary skill set can be obtained by your team. So make sure to remember that when you're choosing the right database. Conclusion. So we looked at a lot of different types of databases. For recap, we started with traditional relational databases where data is neatly organized in tables and accessed via SQL. And then we moved on to NoSQL systems, looking specifically in four categories: key value, document, column family, and graph. And they each optimize for different types of data and use cases. And then we also looked into new SQL databases, which combine the consistency of SQL databases with the scalability of NoSQL databases. After that, we looked at in-memory databases. And then lastly, we looked at cloud databases where managed services handle the maintenance and scaling. So the best database solution, uh, it the solution depends on the specific demands of your application. So you want to check how critical consistency is, how large and varied your data set might become, and what performance or latency constraint you face, which means there is no one size fits all answer. So understanding these options is really important in making an informed decision. Thank you everyone for listening.